I want to talk about these two questions. Explain, number 9, number 10. My intention, what is the right way to solve these two problems? They are similar. These two questions, most part, these two questions, the only difference is the first one for the best case. The second one for the worst case. That's the only difference. So I only need to explain one of the two questions. The other one you can use the similar way. The only difference, you just change the formula. The formula for best case, worst case, different. All right. First, let's look at the formula. Recall a little bit. So we learned for the merge sort, best case, worst case. The best case formula, we know the minimum of m and n. Mn, we know the sizes of two ordered arrays. So when we merge two ordered arrays with the sizes m and n, then the best case formula is this one. So then the worst case formula, you just use mn, but the m plus n minus 1. All right. Then the working part, the steps are very close. So let me talk about the step. All right. 3 order array with these 3 numbers here. Let me use the variables to represent the sizes of these 3 ordered arrays. Size A, size B, and a size C. Okay? All right. So for questions like this, our goal, our goal. So we want to, so here, the goal. We want to find the best solution, right? Oh, sorry. Best solution. All right? That's our goal. All right. So here, there is a, confusion. So many students may have the confusion like this. So best solution, think about. How do we understand this best solution correctly? Because some students confused, confused regarding some words. So the best solution, minimum number of comparisons, right? So we mean minimum number of comparisons. So we always mean that, the best solution. Then, for the worst case, the confusion occurs here. So what's that? Because this time we work on the worst case. Worst case, we know the worst case, right? So the worst case. For the worst case, the number of comparisons is the largest, right? For the worst case. All right. So then some students, so when they work on the worst case, a few students, yeah. Every semester I have a few students like this. So here the confusion part, okay? So all right, so it's not the right way. So there's a confusion. It's wrong, okay? Yeah. Yeah. The confusion part, yeah, because here the largest number of comparison, then they give me the worst solution. Worst solution. Okay? Think about worst solution and worst case. What's the difference? So we targeting the worst case, but some students gave me the worst solution. Can you see the difference? Yeah. So what do we need for the worst case? For best case, no confusion. Yeah, because we want to get the minimum number comparison, right? So no confusion. But for the worst case, there is a confusion. Yeah, because minimum number of comparisons or maximum number of comparisons, some students got confused. All right. So what we need is all right. The best solution for the worst case. Still the best solution, right? Yeah, because nobody wants the worst solution. People always want to find the best solution. Nobody wants to find the worst solution. So the best solution we target the worst case. Yeah, try to compare the different meaning. Okay, yeah, because to answer question number 10, you need to make the decision, which one is the right way. Okay, all right. So let me talk about the steps first. Then in my summary part, then we can come back to, look at this question another time. Yeah. First, let's look at this, step. Yeah. So here, based on our understanding, so we want to try all the possibilities, right? Yeah. Try all the possibilities. All the possible ways. Okay, yeah. Because when we merge these three ordered arrays, there are several different ways to merge, right? Yeah? There's several different ways to merge. Yeah. So among those different ways, we want to pick the one with the minimum number of comparisons. Yeah. So that's our understanding. Yeah. But you have to exhaust all the possible cases, right? Yeah. You cannot miss any of the cases. Yeah. So the first thing, we need to, go through all the possible ways. All right? Yeah, so let me show you how many ways. Okay, all right. First way to merge, all right. Merge A subarray and a B subarray, right? Yeah. And as a result, after the merge, we get A plus B ordered array, right? Yeah. Right? Yeah. Then, to complete the whole question, our second merge, the remaining C subarray, but we have a, new array. So we need to merge these two ordered array to get the, final ordered array. That's way one. All right. Second way. Yeah. And this first way, you get a solution one, right? Yeah. All right. So second way, the solution one, you need to apply that formula. Right. The second way, because you do not have to merge A and B first, right? How about you merge A and C first? So you get A plus C ordered array. Right? Yeah. After that, you need another merge step. Merge this time B and A plus C. Okay? Yeah. Final. Yeah, final. Ordered. All right? Yeah. That's method 2. Third, merge B and C first. So you get a B plus C ordered array. Now you merge the last two ordered array, A and B plus C. Okay? Yeah. Yeah. Solution 3. Yeah. Yeah. Here, yeah, this place, yeah. Solution 2. Then you choose the best, right? Yeah. 1, 2, 3. All right. Now, for question 10, yeah. Can you basically just do the same thing? Yeah. But the only difference is every time when you do the merge, you apply a different formula, this formula. Yeah. So you can get 3 solutions. But in those 3 solutions, you need to pick the best solution, not worst solution. Okay? Yeah. Pick the best solution. Still, for the worst case, you still pick the best solution. Yeah? Because some students, yeah, since you ask me for the worst solution, then I pick the worst solution. I do not pick the best. Do you think it's a confusion? Right? For the worst case, we work on the data that corresponds to the worst case, but when we do our work, we always want to find the best solution. We don't want to find the worst solution. Think about that difference, that key difference. Yeah, because every semester there quite some students. Yeah? So, as I remember, probably 3 to 5 students, gave me the worst solution, not the best solution. Yeah. So this time, I want to emphasize this point, because otherwise you may lose 2 points. In total 4 points, if you pick the worst solution, you will lose 2 out of 4 points. Okay? Yeah? Yeah. Yeah. And we know these 3 ways, that's all the possible ways. Yeah. So that's all we need to compare. Okay? Yeah. Total 3 ways. Yeah. All right. So then, as a summary for these 2 questions, so in our homework assignment, I gave you 3 ordered arrays. In this way, the number of cases is relatively small. So here, we only have 3 cases. So when we work on 3 cases, we can exhaust all these 3 cases. Yeah, because not too much work. All right? Yeah. But in our final exam, I will give you these 2 questions again. Yeah. Similar questions in the final. Yeah. But in the final, think about, I will give you not a 3 order array, I will give you a 5 order array. From 3 to 5, think about how many more cases you may have. 5 ordered arrays. In that one, if you still want to exhaust all the possible cases, too much work, because total 5 cases. If you want to cover all the possible ways, you need to do too much work. Right? Yeah. So that's not efficient. In that situation, that's not efficient. Then we need to find some rule. Yeah. After our homework assignment, these 2 questions, in our review session, I need to give you the rules. Yeah. So when you work on these 2 questions by yourselves, you also think about, what is the efficient way we can use without exhausting all the possible ways. Yeah, because when you work on 5 ordered arrays, it's impossible, going through all the possible ways. Not efficient. Yeah. So we want to find an efficient way. Okay? Yeah. So here I can give you the keywords, the idea, the direction, efficient way. Greedy algorithm. In our module 1, remember in our module 1, evaluating polynomials, that place I talk about greedy algorithm. Yeah. Remember when we develop Horner's rule, greedy algorithm. Okay? Yeah. When we talk about Horner's rule, I introduce the idea greedy algorithm. Okay? Yeah. I use Horner's rule. When we do the factorization, how do we apply the greedy strategy to get the minimum number of multiplications? In that place, I talk about greedy algorithm. Okay? Yeah. 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 But in this first round, these 2 questions, the first round, so even if you do not know the greedy algorithm, because there are only 3 cases, so I ask you, going through all these 3 cases, and you compare. 3 solutions and you pick the best one. Yeah. But in the final, we will move to 5 order arrays. Before your final exam, you need to know how to apply appropriate greedy strategies to solve these 2 problems. Okay? Yeah. So here, I give you some time to think about this question. Okay? Yeah. But in the review session, so I will give you the answer. Yeah. How to apply 2 different greedy strategies to solve these 2 problems. Okay? Yeah. All right. So that's the, hint part I want to talk about before our normal class. Yeah. So any question, just let me know. Okay. All right. Next, I need to switch to the last part of heap sort. Yeah. Yeah. So we have 3 topics. Yeah. So we are here. 8.5. All right. Heap nodes in each level. This time we need to understand the structure of our heap better. Yeah. So let's look at a few questions. First one, number of leaves in a heap. First, we need to understand the concept leaf, right? Yeah, leaf node, leaves. Yeah. All right, describing leaves. Yeah. So let's recall. Yeah. So look at this heap, this binary tree. Yeah. Here in this place, some of the nodes, they do not have any child node. Yeah. So what are those nodes without any child nodes? Yeah. All right, yeah. So those nodes we called leaf nodes. Yeah. That's the meaning. Yeah. So those are the leaves. Yeah. So first, given any heap, we want to count the number of leaves in this heap. Yeah, yeah. All right. Now, here you can see these 3 nodes, leaves, and another 2 here, leaves. Total, there are 5 leaf nodes in this heap. All right. But how do you describe a leaf? So here we use the parent-child relationship to describe leaf. Because the leaf node, if a node is qualified for a leaf node, then it does not have any child node. Yeah. So that's the criteria. Yeah. All right. Let's consider A of I. So this array element is an arbitrary heap node. Yeah. That's our current heap node. All right. Yeah. Then let's look at its child node. Its left child node. Yeah. Left child, we look at the left child node, not right child, because sometimes, yeah, look at this node. This node has only 1 left child node, no right child node. Yeah. So it's better we look at its left child node, A of 2i. Okay, yeah. Yeah. Now, think about, yeah, under what condition this A of I node is a leaf node. Yeah. Although here we, in our discussion, we treat it as a parent node. Yeah. Yeah. But how about we can understand in this way? Yeah. We imagine this node is as a parent node, then its child node is out of the scope. How about that? For a leaf node, we look at its child node, but we understand in this way, its left child node is out of the scope of the range of the indices of this array. How about that? Yeah. Out of the range. The 2i, when we double its index I, 2i, it is out of the range of the array indices. That's our understanding of the leaves. Okay, all right. Yeah. So based on this understanding, now we can write inequality. Okay. Yeah. Because we want to use math formula to describe a leaf node. Yeah. All right. So meaning of no child. All right. How about this? First, the index I must be within the range. Okay? Yeah. So index I. Lower bound is 1, right? 1 less than or equal to I. The upper bound is m. So within the range. All right? Yeah. Here you can see. Yeah. Because some people, yeah. So do not get confused. In our heap topic, the largest element we use n. Yeah. In our previous discussion, our not largest element, our last element in the array. For our usual discussion, the index is n minus 1, right? And here we use n, yeah. Because remember, we cannot use this node, right? We skip this node. Yeah. That's why our range is between 1 and n. Yeah. It's like we shift it. Yeah. We shift the position. Yeah. Because we skipped a of 0. Yeah. In order to address the parent-child relationship. So we cannot use a of 0, this element in our heap. Because we want to use a simple math formula to describe parent-child relationship. Yeah. All right. So the range, but when we double index I, 2i should be out of the range, strictly greater than n. Then we can say a node at index I must be a leaf node. How about that? This understanding. Yeah. All right. So this inequality can be used to describe all the leaf nodes. Yeah. All right. Now we want to count the number of leaf nodes. Yeah. With this formula, now let's do the counting. We want to count number of leaf nodes. How many indices satisfy this condition? Right? How many indices satisfy this condition? Okay? All right. Yeah. So we need to convert this inequality to another more friendly inequality. So what's that more friendly? Yeah. Because we want to describe the I, right? Yeah. So we want to write another inequality that is centered at the I. Yeah. We put the I in the center. Yeah. Here we put the n in the center, right? Yeah. Because from the form of this inequality, you look at, we describe n with its lower bound and upper bound. Yeah? So lower bound and upper bound. But a more friendly version is we should describe the I with lower bound and upper bound. That's better. So we put I in the center. Yeah. So when we put I in the center, all right, yeah. So we can see, yeah. So here we divided by 2, n over 2, strictly less than I, yeah, because we want to find a lower bound for I index. Yeah. So this one we have lower bound. But n over 2 may not be an integer. Yeah. So we want to get an integer lower bound. Integer lower bound, right? All right. Yeah. So then, a better way is we take the floor function, then plus 1. Yeah. So you may say ceiling function. Yeah. Yeah. All right. Yeah. Here, one question. Yeah. Before I move to next step, I want. Yeah. So here, smallest such I that's greater or equal to this lower bound. Yeah. Think about. Yeah. Some students may want to ask, how about we use the ceiling function of n over 2? Is it the same thing? Yeah, because some students may feel, why you do not use upper bound of n over 2? Yeah. The answer is no. They are different, not the same thing. And this way is better. That way, sometimes not correct. Why? Because here we want the strictly less than. All right? Yeah, strictly less than. If you use this way, because when n is even, these two expressions the same, and your I, if your I take a greater or equal to, then you count one more. You include one more number. So that's not right. Yeah. So this way is good. This way, when n is even, you plus 1. Yeah. So less than or equal to this floor function plus 1. Then the original one, strictly greater than, is still correct. Okay? Still correct. Yeah. So be careful here. All right. Now we have the lower bound. Upper bound, this is already upper bound. Okay? Yeah. So we put them together. So we have another inequality with I in the center, and we find appropriate lower bound and upper bound. All right. So with these two bounds, yeah, bounds containing equal sign here, yeah, equal sign. So including those two bound numbers, yeah. So when we do the counting, it matters. Yeah. Equal sign or not, yeah. The counting number will be different. Yeah. All right. Now let me ask you, how many qualified index i's that fall into the range of this inequality within these two bounds? Can you do the counting quickly? Yeah. Yeah. If you have some experience before, then you can write out the answer immediately. Here, let me give you the answer. Upper bound minus lower bound or not, upper bound minus the number that is 1 less than the lower bound. Now, you cannot minus the lower bound directly. If you minus the lower bounds directly, you exclude the lower bound number. But here we need to include the lower bound number. We cannot exclude it. Yeah. That's why we just write the number that's right before this lower bound. Yeah. We cannot write the lower bound number directly. Yeah. So we should subtract the number right before that lower bound. Yeah. So that's floor function of n over 2. Yeah. So this is the right answer. Okay. The formula, the number of leaves in a heap with n elements. Yeah. All right. Yeah. Next, yeah, there is another formula. Yeah. So this one, there is another way to write the same number but we use a different expression. So the ceiling function of n over 2 equals n minus the floor function of n over 2. Yeah. So that is a formula given in our textbook. Appendices. One of the appendices, page 477, you can find this formula. Okay? Yeah. If you want to prove, yeah, it's very easy to prove it. Yeah. So you just look at the two cases. When n is even, you check if they are equal or not. When n is an odd number, then you do another round comparison. Yeah. So very easy to verify this formula. Yeah. All right. Because sometimes this version is more friendly. Yeah. It depends on the situation. Sometimes, yeah, this version more convenient to use. Yeah. So here we have two versions. Yeah. All right. So we complete this first one, but now we want to continue. Number of internal nodes with height 1. Yeah. First, yeah, let me recall the concept. What is the internal node? Yeah. Yeah. External node and internal node. Yeah. The leaf nodes, people also call it leaf nodes. Another name for the leaf nodes. External nodes. External nodes. Yeah. Yeah. All right. Internal, non-leaf node. If a node has a child node, then we call it internal node. Yeah. All right? Yeah. So here you can see all these nodes are internal nodes. All right. Now, we want to count the number of internal nodes. Yeah. All the nodes other than leaf nodes, right? Yeah. We exclude the leaf nodes from all the heap nodes. So we only have internal nodes. All right. Total number of nodes n, among them, there are this many leaf nodes, right? Yeah. N minus floor function of n over 2. Then the offset part, right? Yeah. Internal nodes correspond to the offset part, that is floor function of n over 2. Okay? Yeah, that's simple. Yeah. All right. Next question. So here, second concept, the height concept we need to use. Yeah. Because here we need to count the number of internal nodes with height 1. Yeah. So what's the meaning of height? Yeah. Here, from the tree. Yeah. So look at this node. Look at this node. When you start from this node, then you want to get to the bottom, so you need to follow a path. So this is a path. Path with one edge. See? One edge. So this path, you only need to follow this path with one edge, you can reach the bottom. Okay? So the number of paths you need from the current node to the bottom, yeah. But the path should be the longest path. Yeah, so here. So when we count the height, okay, yeah. So the several things we need to be careful, yeah, because many students, when working on heights, so they understand in the wrong way. Yeah. All right. So current node, yeah. So we need to follow longest, because you may have more than one longest paths. Okay, follow a longest path. To the bottom. Yeah. Then you count the number of edges. Count the number of edges of this longest path. Okay? All right. For example, when we look at the root node, okay? Look at the root node. root node, yeah, you want to find the longest path to the bottom. Yeah. So this one is the longest path, right? 3 edges. This path, 3 edges, right? Also longest. And this path, 3 edges longest. But this path to the bottom, yeah, so this is the bottom, okay? We also treated this as a bottom because when you reach a leaf node, then we say we hit the bottom, okay? Yeah. When you reach a leaf node, that means you hit the bottom, okay? Yeah. All right. So, but this path you only have 2 edges, right? This, yeah, we call it length. Yeah, the number of edges. So that the concept that people call the length of the path. All right. Yeah, the length equals 3 and also 2. All right, but you use the longest path to measure your height. Okay. All right. So that's why this root node you can call it the height is 3, not 2. You cannot use the 2 edges, that path, to count your height number. All right. Yeah. So then for the leaves, the height is 0. Yeah, because all the leaves, we treat them the bottom level. So the bottom level, no height. Okay. All right. So the number of internal nodes with height 1 now, yeah. So what are those nodes? These 3 nodes in the red circle, okay? 3 nodes in the red circle. These 3 internal nodes, they are internal nodes, and their height are 1. Yeah? Yeah. Based on our definition of the height. So their height are 1. Heights are 1. Okay, all right? Yeah. So after you understand this concept, yeah, because when I did a grading before, many students, they understand the height differently. Yeah. So here, I show you the typical errors, people have. Yeah. Height. Okay, all right. Many students count the height with respect to top, not bottom. So now we count the height number with respect to the bottom, right? Yeah, but many students count with respect to top. Okay, so like the height, then this height they count. So the number of edges 1, all right? So this height, the distance, edge number, 2. That's the wrong way. Okay? So that's not the right way to define the height number. Okay? Actually, this understanding, we use a different concept. We do not use height. We use depth. Depth. Yeah. Like underwater, right? Yeah. So this level, this top level, like surface of the water. So below water, the depth, what is the depth number? So we use a different concept. Yeah. So do not get confused. The difference between height and the depth. Yeah. All right. Yeah. So now we need to count the number of internal nodes with height 1. Now we have the experience counting number of leaves. Now we just need to do some adaptation so we can get a similar inequality, upper bound, lower bounds. Then we do the counting. All right, so let me do it quickly. Yeah. This time, how to describe an internal node with height 1. Yeah, so we use this way. Yeah. First, they have children, so they are internal nodes. Yeah, they have children. But because we only want height 1 such nodes, so their children must be leaves. Yeah. Their children must be leaves. So that's the way we use. to describe these nodes. Yeah. All right. Their children, we know the index left child, right? Yeah. So left child. 2i, its left child index 2i must fall into the range for the leaves. Yeah. So this is the range for the leaves, upper bound, lower bound. Okay. But for 2i, okay, not I. Yeah. Yeah. Then, so let's do the simplification. We divide it by 2. Yeah. All right. Divided by 2. But our upper bound, lower bound, when we do the division, we want to use integer expression, right? Yeah, we want to use integer expression. Yeah. And when you do division by 2, sometimes it may not be the integer expression, so you need to convert it to integer expression. Yeah. The upper bound easy, you just use floor function to convert. The lower bound here, how do you convert? Right? Yeah. How do you convert? Yeah. Divided by 2 may not be, yeah. So then you need to take ceiling function, right? Yeah. Ceiling function. Yeah, but why we get this? Yeah. All right. So here I want to explain. Yeah. Yeah. So original version should be the ceiling function like this. Yeah. But here I want to say, yeah, after simplification, yeah, so this is the simpler version of the original version. Yeah. How to see it? Yeah, you may ask me how to see it. Yeah. We can prove it mathematically. Yeah. So when you prove it, you need to do discussion. Yeah. This time you need to consider m is multiple of 4k, and a multiple of 4k plus 1, 4k plus 2, and 4k plus 3. Okay? Yeah. So you need to look at these 4 cases to verify this formula. Okay? So then you can prove it. You can verify it. All right. So now here the answer. Yeah, because now we have the range for the internal nodes with height 1. Now let's count the number of internal nodes. Yeah. Count it. Yeah. So using the same way we count the number of leaves. Yeah. Upper bound minus the number right before the lower bound, right? You cannot minus the lower bound directly. Yeah. But the one right before the lower bound. Yeah. All right? So this is the counting number. So this many number of internal nodes with height 1. Okay? All right? Yeah. Then, remember, in our number of leaves, we have second version. Yeah. But this time, we have another version, but the difference is this place is inequality, not equal sign. For our number of leaves, we have the equal sign, right? Yeah. So we have 2 versions. Those 2 versions are exactly the same. But here, we have 2 expressions, but this expression, there is an unequal sign. Yeah. So when you do the verification, you will see sometimes these 2 expressions are slightly different. Yeah. But why we still need inequality? Because when we do the estimate, sometimes this version is more friendly, simpler, more friendly. And then later, when we estimate the total cost, we need to use this version, more friendly version. Okay? Yeah. All right. Yeah. So we finish this problem. Yeah. But the next one, we want to get the general with any height. Yeah. 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 So we need to generalize the result. The number of leaves, this formula, yeah, all right, corresponding to height 0. Number of nodes with height 1, that's the range. This is the range. Yeah. And the counting number, this is the counting number. All right. Can we, by our logic, we can derive or guess. Yeah, here. Yeah. to get the formula quickly. So we want to make reasonable guess based on the structure of these formulas. Yeah. All right. So with arbitrary height, so let's use this formula as the reference. Yeah. The range this time when we do division, n over 2 to the h. Yeah. Here, this version, 2 to the first. The height number is 1, right? Yeah, so this is the height number, h. Here we replace the height number, special number 1. This time we use the general h. Yeah. So the range is this. Then the counting number of nodes in this range, this many. That's the counting number. Okay? All right. Yeah. So after we have this formula, then we are ready to estimate the building cost. When you build a heap, how many operations, how many comparisons, how many, because when you need to fix the max heap property, right? Yeah, you need to do the heapify operation by fixing the violations of max heap property. Those nodes you need to, so you need to do comparisons. So we count the number of comparisons. Yeah. So next topic, building cost of a heap. All right. Now, so we combine the cost of all heights. Now, because when you fix a node, we need to consider the worst case, right? Yeah, worst case. Yeah. So we do remember the triangle. We work on a local triangle fixing. So we move the dirty node down to the bottom, right? Yeah. So the worst case, we always imagine that a dirty node should reach the bottom. So that's the worst case. All right. Cost of max heapify for all nodes of height h. Yeah. All right. Yeah. So what is this number? Remember, in our counting number, so the number, oh, all right, so here, so what's that? I need to give it number of internal nodes with height h. This number less than equal to this one, right? Yeah, inequality. It's an inequality. Okay, yeah, that's an inequality. Less than or equal to. Yeah. All right. So that's the number. Yeah. So we estimate. So that's the upper bound for these nodes. All right. Then let's imagine for each such node, how many moving down operations. Yeah, we need to swap, right? We need to do comparison. Then we need to do swap operation. Yeah. Look at the number of swap operations. Yeah, let's use the swap operations. Yeah. All right. Yeah. Later when we switch to comparison, comparison should be a constant multiple of swap operation. Yeah. The difference is constant multiple. Yeah. All right. The swap operation, the worst case, you need to count the number of edges, right? For the longest path. All right. Yeah. Longest path. Yeah. Because the height is h, right? Yeah. So the number of swap operation corresponds to the number of edges, right? That's the height number. Okay? Yeah. Here we use big O. Yeah. Constant multiple, Yeah. Constant multiple. So for each such node, we need a constant multiple of h cost. That's the cost estimate. So the cost containing swap, comparison, everything we need. Yeah. So that's the cost. All right. Then you do multiplication between these two numbers. All right? Yeah. But when you do multiplication, you need to include all the nodes with height from 1 to the top one, the root one. The root one, the height is this. Root 1. Yeah, floor function of log base 2 of n. Yeah. Floor function. All right? Yeah. 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 Skip the leaves, yeah, because for the cost, when we reach the bottom, we stop, right? So for the nodes at the leaf level, there is no cost. There is no fixing cost because you do not need to fix anything, right? Yeah. When a dirty node hits the bottom, then it becomes a clean node immediately. So no fixing cost at the leaf level. All right? Yeah. So based on that understanding, we can look at the total cost summation covering all the height numbers. Yeah. For each high number, yeah, the upper bound, right? Yeah. So that each such internal node, you need this much cost. So that's why you have a multiplication. Now we need to estimate this summation expression. All right. Yeah. So the estimate, yeah, because here, this seeding function quite annoying, right? Yeah. In our calculation, we don't want to look at all the possible cases. Yeah. But the seeding function may give us a lot of cases. Yeah, quite annoying. So we enlarge, yeah. So, here we do the estimate. Yeah. So we enlarge that seeding function expression to this expression, then much simpler, right? Yeah. Because no case discussion needed. No case discussion needed. Yeah. Yeah. But we need to make it a little larger. So +1, make it a little larger. All right. Then, so let's estimate the summation expression. Yeah. There are two parts, the summation. Yeah. So the first part, second part. Okay? Yeah. So we split. Yeah. Two terms inside parentheses, we split them. So we have two summation expressions we want to estimate. Yeah. But the second summation, this second one, very easy, right? Yeah. Let's estimate the second summation expression first. Yeah. The easier case should come first. All right? Yeah. All right. So look at the easier case. Yeah. So we apply, yeah, because sum of consecutive integers, right? Yeah. So big O we can treat as constant multiple. This big O, you just in your mind, you just think about there is a constant C. Capital C times H. So you can take that capital C out. Okay, all right. So inside, yeah, so you have this, yeah, because 1/2 for the big O notation, the 1/2 is not important. We can ignore it. Yeah. So here we only have this. So you can see this one we can simplify to big O of log base 2 of n, but it's a square. Okay. Yeah. It's a square. Yeah. All right. Yeah. So that's this one. Yeah. This one square. All right. Yeah. That's the second summation formula. Estimate. Yeah, this one. So we put it aside. Yeah. All right. Let's look at the first one, the main term, yeah, the most important one, the first one, harder. Yeah. All right. In this expression, you can see n, there is an n there, but this n is a constant, right? It's fixed number. Yeah. So when we calculate this summation expression, that this n never changes when we go through all the terms, right? Never changes. So we treat it as a constant number, so we can factor it out of the summation notation. Yeah. After we take it out, so we need to calculate the summation expression. This one. Yeah. All right. Yeah. All right. Then, yeah, because the upper limit of this summation still annoying a little bit, right? Yeah. The floor function not very friendly, and the log base 2 function also not very friendly. Okay? All right. So we want to get rid of the, annoying part. So we replace it by infinity. Here you can see we are very generous, right? We are very generous. Yeah. Yeah. Because we just look at the infinite summation. Yeah. So it will be larger. Yeah. So we allow, some more terms here. Yeah. All right. So let's estimate this infinite summation question. Yeah. All right. All right. That means we need to calculate this expression. See how large it is. Okay. All right. Yeah. Here, let's do the calculation. Yeah. Our goal, we want to calculate S equals this expression. So we need to explore its structure. The structure here, you can see all the denominators are power of 2. So that's a nice property. We want to take advantage of it. Yeah. Power of 2. All right? Yeah. Because when we double the S, multiply 2 both sides, all the fractional terms at the right hand side still power of 2, right? Denominator. Yeah. So denominator still power of 2. Yeah. Same structure. Yeah. But you can see the numerator. Yeah. So the difference at the numerator. Yeah. So you compare 2 corresponding terms with the same denominator. You compare their numerator part. You can see 1 and 2, the difference is 1. Second pair, the difference also 1, right? 2 and 3. Yeah. So if you do the comparison all the way down to the end, all the way down, you can see the difference of the numerators always 1. Yeah. So that's a nice property. Nice observation. Yeah. Then we take subtraction. Yeah. We take subtraction. S equals. Then we collect all the fractions. You can see the denominator consecutive power of 2 numbers, and the numerator always 1. Then this summation is very easy. Okay, so it's a geometric series, and we have the formula calculating geometric series. So the answer is 1. Very easy to see that the answer is 1. This, yeah. Then S equals 1. All right. See, now we can look at the building cost for a heap. When we build a heap, this is our main term. Yeah. The main term, after we factor the n out, the inside part, so we just complete the estimate of S. That's 1. So 1 times n. That's why its building cost is bigger of n. All right? The second term, although we also need to consider the second term, but the second term, when you compare with the first term, much smaller, right? The first term dominates the second term. Yeah. So for that reason, we just drop the second term. Yeah. So we only look at the dominant part. Yeah. So that's the big O of n. That's the building cost. Yeah. How much, comparisons or, basic operations do we need to build a max heap? That's the building cost. Okay? Yeah. So that's pretty good. Yeah. So we can accept it. The cost is not very high, so we can, pay. Yeah, we're willing to pay this much to build a max heap. Yeah. All right. Then the last question, 8.7, heap sort efficiency analysis. Yeah. So we have a few minutes. Yeah. So let me just do one slide. Okay. Do one slide. The remaining 1 or 2 slides we can complete next time. Yeah. Idea of heap sort. Key observation. So now we're ready to run the heap sort. That's the last step. Yeah. Ready to run heap sort. All right. Here we imagine we have a max heap. So this is a max heap already. Okay. Yeah. Yeah. So this is a max heap. Yeah. All right. Satisfying the property. Yeah. All right. Now you can see the largest element must be at the root position. Yeah. Must be located at the root position, maximum. Yeah. So that's based on the max heap property. All right. Yeah. Then you can place it in place immediately, right? Yeah. Because the maximum number, the final location of the maximum must be at the end of the array, right? Yeah. So you can put it in place immediately. Yeah. First, after we get a max heap, let us put the maximum in place by one swap operation. Yeah. Yeah. Suppose this is our underlying array. Yeah. The root location, the heap location for the root is the first element, right? Yeah. But in our final destination array, the maximum number should be at the end of the array. Yeah. So we just do one swap operation. We will make it happen, right? One swap operation, we will put the maximum element in place immediately. All right? Yeah. All right. But after that, how to work on the remaining elements? Yeah, we just put one element in place. Our goal, we need to put all the elements in place. So how to handle the remaining elements? Yeah. Let me complete it next time. Okay? Next time I use approximately 5 to 10 minutes to complete the remaining part. All right, that's it.